Type soundness is a critical property for type systems. Here's one example of a strong type soundness theorem. This one says that if the expression E is well typed in the empty environment, then running E never produces an error. This is a strong theorem because it's saying that types predict every sort of way that the program could go wrong. In practice, this is often too strong. It's a lot of work to use types to show that all those errors can never happen. For example, suppose we have division in the language. We might want division by zero errors to be okay, in which case we would weaken the type soundness theorem to say, if our expression is well typed, well then, running E never produces an error that's not a division by zero error. We'll say that this divide by zero error is okay because we don't want to go through the work of proving to the type system that every denominator in our program is a non-zero number. We'll let that one get checked at runtime. But other kinds of errors our type system will rule out. So in general, a type soundness theorem rules out a certain class of runtime errors. And this is really the value added by the type checker. Yes, it'll catch some bugs and typos, but more importantly, it'll make sure that we never have to worry about some sorts of errors happening. We'll never need to debug the errors that are ruled out. Of course, we get that guarantee only when the language really satisfies the type soundness theorem. If soundness fails, that means we have some kind of a bug in our type rules. Right now with typed Mo, unfortunately, our language is not sound. First off, we have a kind of bug in letrec type checking. This program here is well typed, but if we run it, we get an error. We say letrec f with type int is equal to f. And the problem is this f here is using f before it's been defined. We have a use before initialization error. One way to deal with this bug is to change the grammar for letrec, and some languages do this. They'll say letrec must have a function on the right-hand side, so that way we can't possibly use a symbol on the left before it's been bound, because this function will immediately evaluate to a closure value. As we've seen before, though, this kind of rule rejects some useful programs that still don't have use before initialization errors. And so an alternative, which we'll go with for typed Mo, is to say we'll adjust the soundness theorem. We'll say that these use before initialization errors are okay to happen at runtime, and this means we weaken type soundness. Let type also has a bug, and this one is a bit more serious. Here's an example. This program is well typed, but it should not be. First, we say f is equal to the result of this expression. This expression eventually produces a function, but before that, it has a local let type declaration, which binds foo. Now our function down below expects an input of type foo. That function is now bound to f, and then we go down below. We call f, and the argument is the result of the second let type expression. We have a second let type, which also binds foo, and in the let type body, we create an a variant. So an a is a foo, and this a has a function inside, int. Our type checker says, well, this is a foo, f is looking for a foo, so it's okay, this application might just work out. But if we look up above, the foo that the function expects has an a variant that takes just an int argument. So things are going to go wrong here. We'll match on our input, we'll see that it's an a, then return the n value on the inside. This n is expected to be an int, but from our argument down below, it's really a function. So if we were to run this, we'd be adding 1 to a function. We don't want that to happen, not in our typed interpreter. So what to do? One solution is to say there can be no local type declarations. They all need to go at the top of the program, just like our class declarations all had to go at the top. This is a bit extreme. An alternative is to say, don't let the newly defined type escape from the let type expression. We've got a let type foo up here. We need to make sure that whatever value we return doesn't depend at all on foo. So this function here would be rejected by the new rule because it's a function that takes foo as an input. That means f would have foo in its type, and that's a kind of escape. We don't want the escapes. More formally, solution 2 means we need a different typing rule for let type. In addition to extending the environment and doing the checks that we had before, we also need to check that this newly defined type D, this does not show up anywhere inside the type tau0 that we have for the expression body. Let's go with that. We use solution 2 to fix the type soundness bug that we have inside let type.